because you have an accommodation. This is super important. I'm going to email you this time because you are in ACB 214. Super important. Do not, I repeat, do not come to Berkeley. Go straight to ACB 214. Bring calculator, researcher mind. We're going to talk about that today. Scratch paper. Grades will be posted by the weekend. And then enjoy your spring break, because we hammered them really hard before the midterm and you did really well on them. I'm not going to focus on assumptions on this one. That's been mastered. I want to focus on the stuff that's newer. Multiple regression is on this. Multiple regression with main effects only and moderation, because both of those are thinking about like, how do we make sense of the world with regression? Things interact, they don't. Both of those are on, and then obviously binary logistic regression. APA reminders. Values that end in 5 or more, round up. Values that end in 4 or less, round down. P-values are rounded to 3 digits. All numbers other than p-values are rounded to 2 digits, even if they end in 0. I had to go in manually and add 46.3 as an option because people didn't round to 2 digits. If the number rounds to 0, this is an important one. If the number rounds to 0, include all the zeros until the first, what we call significant digit. The first significant digit in that intercept question on the check-in was 3. Round it to the first significant digit. And then this is a big one. It asks the question, how much variance was explained by the moderator? Generally, the rule of thumb is do all your calculations before you round and only round your final answer. You'll see that in the deck today. Values that can be greater than 1 get a 0, like a B, and values that can't be greater than 1 don't get a 0. Betas, Ps, classification rates, etc. And then decimals versus percent. It said what percent of the variance, and people gave the decimal. First of all, arose by any other name, what is a model? All of these are models. One of the things that you need to be able to do is to translate models into different languages. Coefficient table, that's a model that corresponds to here, a theoretical model or a drawn visual model, which corresponds to a hypothesis, a model in written form, which corresponds to a model specified in R, which corresponds to a purely theoretical model, a model that looks like this if you want to label it, a beta version of the model. This is our standardized version of the model, the simple slopes depiction of that model, and the unstandardized equation of that model. All of these, you can even think about like how many versions are there. All of these are the same model. And you want to feel comfortable going back and forth between these types of models. I shouldn't say types. I should say, I don't know, translating models. Yes, between different types. Questions at all about this? We've specified 4 types of models. Simple regression, multiple regression that has interactions in it, and binary logistic regression. For the general linear model, that is involving an outcome, which is continuous, predicted by a linear combination of predictors, not binary logistic regression. Binary logistic regression is not under the general linear model. Let's go to this assumptions question. We did relatively well on this, except for most people missed independence of observations. A lot of people said that independence of observations does not apply to simple regressions. It does. Here's how you talk about independence of observations. Let's say that we're studying the effect of, I don't know, exercise, happiness. And you all are in the study. Hannah's score should not be in any way related or influencing JJ's score. What would, or any type of, not that Hannah herself is influencing, but their actual scores should not be related at all. What would be a circumstance in which they would be related? That would be like very, very related. Hannah and, but let's actually take that example. If we're studying exercise and Hannah, JJ, Shane, Victor, I don't know, Lindsay, Alana all go to the same gym, and then everybody else, you all go to a different gym, guess what? Your scores are related. Why? Because the gym you go to could be influencing your happiness or influencing your exercise. When we have data that is clustered like that, the observations are not independent, in which case regular regression is not an appropriate option to analyze the data. we have to use a multi-level modeling approach. It's not a statistical thing you test, it's the nature of the data and how you collected it. Another really common violation of independence of observations would be longitudinal data. If I'm collecting like Priscilla's happiness scores 4 times, well, then obviously her score at time 1 is related to her score at time 2. I can't just treat those as separate observations. This is one where like, you know it going in, but if violated, it's actually the one of all of these assumptions where you have to abandon multiple regression and analyze your data with a different approach.
For example, like in our DA that we just did, the study looked at everyone as individuals and then brought them over to be mock juries. Would the mock jury in that instance be an independence of observation issue?
Totally. If you brought, if they were all on different juries, like randomly assigned, no. But if you ended up, let's say with like, I don't know, let's say your sample had 60 people and 20 of them were on one jury, 20 of them were on another jury, and 20 of them were on a third jury violation, I would run that as a multi-level model.
Thank you.
Yeah, good question. Anything else about that one? And like I said, I'm not even sure there is even anything about assumptions. I would have to, if there is, it's one question. When I am looking at else's data and else's research and they give me their results, how do I make sense of it? Which is basically what you're doing on the exam. Rather than thinking about it as an exam, you want to think about it as a bunch of different research studies that people are handing to you that you have to make sense of. This is my first answer to the question, which is y'all need to pull back a little and see the forest for the trees. Here's example 1, moderation. If you have a relationship between X and Y and it's moderated by Z, and it's asking what's the relationship between X and Y when Z is average, and then it's asking what's the relationship between X and Y when Z is high. Can those be the same? Like forest. What's the definition of a moderator? Changes the relationship between X and Y. By the whole idea of moderation, big picture, those can't be the same. The relationship between X and Y should not be the same when Z is average versus low versus high. But if you're tunneled and you're not thinking like, wow, Z is changing the relationship here, you could end up putting the same value. Here's another example. You're working with betas and it's asking for a slope and you put down 1.32. What's the range of beta? 0 to 1. If you can't sketch it, it's not. First thing that you do, you're going to read the background. And I would add ID the research question. Draw the model, but draw the model, not the purely theoretical. Draw the way we practiced on last time, where it's going to allow you to label every path. Remember that the number of coefficients, not the intercept, other than the intercept, the number of coefficients is equal to the number of relationships, which should be equal to the number of arrows you have in your theoretical, helpful theoretical model, let's call it. Then you're going to annotate your model with your coefficients. If you have access to betas, use them. Why? Because betas are easier to understand in terms of a relationship. But like on the check-in, you're given an equation only and it's unstandardized. Then you got to use the B's. That's it. Then write out that full model in equation form. Translate it from whatever it gives. Obviously, if it gives you the equation already, you're set. You don't have to do that. But translate it into the equation if you don't have that. Then if it's a main effect model only, you're done. But if it's a moderation model, do 2 more things. Go for the simple slopes yourself, because you can't know the research findings until you know the simple slopes. This idea of wrapping your head around the research can't happen unless you figured out how are X and Y related when Z is high and low, or when Z is not this reference group, but this group. Do that first using your model. And then if you have the betas, you can't do this if you don't have the betas, but if you have the betas, sketch those. You can visualize it and then tell yourself the story. And for goodness sakes, do all of this before what? Not answering the question, even looking at a question. If they handed me their data, the very first thing I would do is all of this before I'm ever like, what's the slope between X and Y when blank is high? Don't let the questions guide you into tunnel vision. What does this actually look like in all of the models that we've run? Here is a main effect model with continuous only. We're going to draw the model on the, this is the purely, over here on the left, I have the purely theoretical. Let's call this the helpful theoretical. Work conditions. label it with your B and beta. Support, label it with your B and beta. Intercept can go over here. It's just the predicted job satisfaction if we were to plug in zeros there, centered or uncentered. Here's what it looks like with a continuous and a categorical predictor. This is what the purely theoretical looks like. But if you've got more than two levels, if it's a 3-level categorical, this drawing on the left is not helpful. Why? What would you put here? Why is the drawing on the left not helpful? Because it would mush all the dummy codes. You have 2 dummy codes. You're like, which of those dummy code slopes, B3 or B4, would I put on that line? Draw it in a helpful way where you separate out those 2 dummy codes into their actual terms in the model. You have, you have D1 here and D2 slope here. Now, if we have main effects and interactions, let's look at just a continuous predictor and a continuous moderator. Pretty easy. Beta, main effect of work conditions on job satisfaction, B1. Main effect of support on job satisfaction, B2. And then the change in slope, B3. If you want to remember, I like writing a delta. It's not a slope, it's a change in slope. And then, guess what? You can calculate your simple slope super, super easily there before you ever look at any question. When support is average, it's like it's gone. It's just this. When support is high, you add the change. When support is low, you subtract the change. You're done. You have all your simple slope answers there, and you can sketch them. That's enough to figure out, wow, what does happen to job satisfaction from working conditions based on support? If you have a 2-level categorical moderator, this is how I would label it. It's exactly the same as a continuous, but I would add one thing. I would indicate for yourself what's the reference group, and I would remind yourself that the only values you can plug in here are 0 and 1. Why did I do that? But where is this coefficient what is this coefficient gonna end up as? It's gonna be a constant. This reminds me that the only values this can be are either 0 or B itself, which is B times 1. And what does that get added to? The intercept. It's a reminder that yes, it's a slope, but not really. With a categorical variable, that's actually changing my intercept. And then if we have and then you can calculate it. Voting history, likelihood to vote for Democrats, which is our reference group, is just our original slope. And then for Republicans, we just add on the change in slope. There's no low high here. And then the last one is what we do if we have a 3-level or a 4-level, if you wanted to be crazy. I'm not gonna make you do that. Here's your purely theoretical. Again, what would you put here? Because you have 2 of these and you actually have 2 of these. You can draw it like that too if you want. You can draw it like that if you want, or you could draw it like this on the where you have 2 changes in slope. How do you do this? Remember, again, these are going to change the intercept. I just plug in like 0 and 1 to remind me of that, because those values can only take on 0 or 1. And then I calculate the simple slopes. The relationship between voting history and likelihood to vote for Dems is like both of these moderators were to evaporate from my model. That is just the original pink B or beta. And then to get Republicans, I just add on the moderator term on the Republican line. And to get independents, I just add on the moderator change from the independent line. And boom, you have your simple slopes, all before you ever touch questions. Questions about this. I got this question, what would the model look like if it were binary logistic regression? Identical to everything we just looked at. The outcome, we could make this a binary logistic regression. The only difference is likelihood to vote would be yes or no. Yes voting, no voting. But the model would look identical because everything on the left is just regular multiple regression stuff. It's only the outcome measurement that changes. Yeah.
Not related to what you just said.
That is the coding scheme in the data, but they actually are both 0 Dem, 1 Republican.
Okay.
And 0 Dem, 1 independent, because it's
Yeah.
not looking at both. It's
Yeah,
just looking at that one. Yeah, good question. They look identical. The process is identical. Research question, draw your theoretical model, examine your data, visualize it, check assumptions, specify and estimate your model, evaluate model fit, run additional models and compare them, and then label that theoretical model with your final coefficients and interpret them. No different. What is different are the units and types of statistics we get from our model. We're not dealing in units of Y, we're dealing in logits. We don't get an R squared or an F-stat, we get chi-squared, but they're super analogous. Everything in regression has like a counterpart, and the working is the same in the sense that the regression equation looks the same with the exception of the outcome. Here we have multiple regression equation where we have continuous or categorical predictors, and we're predicting a continuous outcome. Ultimately, what we want to do in binary logistic regression is actually predict probabilities. We want to predict the probability that will win the game or the probability that will stay another year. We call that either the desired outcome or the target outcome. That's usually the one we label 1 compared to 0. It's whatever we want. What's the probability of this thing we want to happen happening? Ultimately, what we really want to predict is probability. But in order to do that, we can't just keep it like this. Why can't we keep it like this? Because the actual data is either yes or no. And you can't, when you're trying to predict with continuous, with OLS, ordinary least squares, if you're trying to predict 0, 1, you have dot, 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 let's say, and dot, dot, dot. If your data looks like this, and you try to fit a line, what's the problem here? Ask this question, like, the problem with OLS is that it assumes our data are continuous, which means based on an OLS model, if I'm here, I'm going to predict above 1. The probability of you staying is 1.3. That's impossible. OLS is continuous. It goes on forever, but we can't predict above 1 or below 0. We need a function that stops at 1 and stops at 0. Probability can't stay. We have to use continuous on this side to get to probability, and that is the logit. A logit is the natural log of the odds, which is a continuous value we can then turn into probability. That's the key. Now, logits on their own are not interpretable. We know that. But we care about predicting logits because logits can be turned into probabilities. The logit is what we use for actually predicting a continuous value, but then we can translate that back into probability. And that has to do with the question that you asked about visualizing. Here's where I'm going to go deeper than you need to because a bunch of people ask this question. This is called the sigmoid curve, and it's a graphical representation of our model, of our function, but it's already, notice if you read the sigmoid curve, the y-axis does not say logit. Do you see that? We're not predicting logits. We're predicting probabilities. What it's doing is it's taking the logits and transforming them already into probabilities. What is this predicting? This is age predicting the probability of disease. If we were to draw the model, it's exactly the same as any other simple regression. Disease equals B sub 0 plus B1 age. What's the only difference? Logits. That's it. That's the only difference. We're just predicting logits instead of disease on a scale of 1 to 7. That's it. It's the only difference here conceptually. How do we read this? What is the probability? Here's where all the data is clustered. When age is low versus when age is high, what's the story here based on the data? Yeah, as you get older, the probability of getting whatever disease this is testing goes up. The closer that this curve, the less curved this line is, means you're going to have data. If your data is really spread out, your curve won't be as S-like. If everything is really tight, like here and here, you're going to have a huge bend. Yeah, good. We good with visualizing? Yes, online. Any more questions? This one was fun. In binary logistic regression, we don't have betas. One of the things that we use to figure out the impact of predictors are odds ratios. This question asked, which of the following is a stronger relationship between predictors and outcomes? An odds ratio of 0.5 or an odds ratio of 2, or they're equal. This one was tricky for people. Let's start with remembering what an odds ratio is. An odds ratio is the odds of one thing happening compared to the odds of another thing happening. The odds of staying versus the odds of leaving. The odds of winning versus the odds of losing. The odds of passing compared to the odds of failing. Let's look at both of these odds ratios. Decimal odds ratios aren't very helpful because it's the ratio of two events. If we start with an odds ratio of 0.5, That's an odds ratio of 1 to 2. If this is event A and this is event B, how do you interpret that? Event B is what? Twice as likely to happen as event A. How about an odds ratio of 2? Event A is twice as likely to happen as event B. They're exactly the same amount of strength. It's just which outcome is going to happen. That make sense? Does that clarify?
Yes.
I
It's
can
not,
see inside your brain.
but it's not quite the same if you add context.
Correct. Sure. It's not, if you asked which of the following indicates a stronger likelihood of staying, the answer would not be they're equal. But that's not what it's asking. Yeah, it's asking in terms of an event happening, these are actually the same. It's just talking about which event is going to happen. If these were actually comparing the same event, like exactly the same, then it would be like this. This is B and this is A. In this case, B is 2 times, let's do it that way. How do you interpret this? B is 2 times more likely to happen, twice as likely to happen than A. Guess what? B is twice as likely to happen as A. Same ratio. But yes, with context, it would not be the same. Cool. Questions at all
Yes.
about this one? Line? Lisa,
Yes.
yeah.
Thanks. Would the odds ratio of 0.25 be the same as an odds ratio of 4?
Yes.
Yeah, thank you.
0.25 and 4. 1 over 4, 4 over 1. Event B is 4 times more likely to happen than event A. Event B is 4 times more likely to happen than event A. All you're doing is deciding which event you put on top and which event you put on bottom. Yeah. If you're interpreting it, what's coming out of your mouth is exactly the same except for the event. Event blank is 4 times more likely than event blank. The strength is the 4 times more likely. That's the same. It's just which event. Good. How do we actually read model fit? This is where the concept is the same as regression, but the distribution we're working with is different. In regression, we work with an F distribution to test significance of the model. This part. In Bilo-Ray, we work with a chi-square distribution. But both of these orange boxes, whether this is in Bilo or regression, are testing whether your model is significantly different than a null model. So if you want to be specific, this is the difference. This is the difference between your model and the null model. Where's your model chi-square on here? Yeah, this is your chi-square of your model. You have your model, and then you have the difference between your model and the nothing model. Don't worry about that. That's all I'm going to tell you. What's the closest thing we have to an R squared here?
Accuracy.
Yeah, here. Remember, if I gave you a multiple regression model and was like, how good is your model? You would be like, it explains 27% of the variance. You'd go straight to R squared. If I gave you this model and was like, how good is your model? You would be like, it predicts correctly 77% of the time. It's like, that's the analogous stat. Accuracy is the same thing. Asked about the word accuracy is the same thing as classification success. It means using this model, if I took 100 people and I looked at their tips and I said, you made 400 staying, you made 300 leaving, you made 600 staying, you made 200 leaving, and I did that 100 times, I would be 77% of the time. That's what that means. You can end up, we've seen where, I'll go to on the next slide. You can, and before we go to the next slide, you can report either. You can report the difference between your model and the null model, or your actual model chi-square. Either way, you should report your classification success rate. I'm going to answer in one sec, Brady. Now, comparing models is identical to multiple regression. You've got one model, you've got a second model. This is closer to the null. This is way further away from the null. We compare those and it's significant. Model 2 is better than model 1.
It may not matter for the exam, but does parsimony count when you're talking about Bilo-Ray?
100%. Bilo-Ray is no different from regression when you're doing model fit and model. It's identical. If the model isn't better according to significance, don't go with a more complicated model. Go with the simple model. This is really important. We use the model to choose models, not the classification success rate. Here is why. Here are 2 models, model 1 and model 2. What are these predicting? What's our Y unit? Logits. But what are those logits actually getting translated into? Probabilities. They're getting translated into probabilities. Ultimately, what I want to be able to do with my model is feed in hours and tips and eventually come up with the probability that you're going to stay. Probability can be anything from 0 to 1. There's a ton of range in there. Classification is what? It's binary. Classification success or accuracy is forcing a decision. It's saying you're staying, you're leaving, you're staying, you're leaving, you're staying, you're leaving. It's not nearly as precise as probability. And it comes up with a threshold, which you can actually change to determine when am I going to decide stay or go. But there's much more nuance in predicting probability than there is choosing stay or go. And your model, in this case, your second model can be better, even if, let's say, model 2 was like 81%. Because ultimately what our model is doing is not forcing a choice. It's predicting probability of an outcome, which is gives us far more range of outcomes than just stay or go. Does that make sense?
Yeah.
Yes, even though the classification success rate might be lower, we evaluate model fit exactly the same way that we evaluate model fit in regression, regular regression. Let's look at the coefficients. Here, a lot of people ask, like, what does the intercept mean? The intercept means the same thing the intercept always means. It's the predicted Y value when all your X's are 0. If you didn't center your data, it's when those are truly 0, like no hours, no tips. If you centered your data, it's the predicted Y with average hours and average tips. Centering is up to you here. Why? There's no moderation. It's just a main effects model. Now, I would center because 0 hours and 0 tips seems silly, but maybe it has 0 hours and 0 tips. And it's the predicted Y, but what units are we predicting in? Logit. The only difference is that it's the predicted logit for who works. In this case, it's centered, average hours, average tips. Yeah. How do we interpret the B? Same way we interpret the B in a regression. For every 1 unit increase in hours, holding tips constant, we'd expect an increase in Y of 2.54, except it's 2.54 logits. That's the only difference. When interpreting this, the only difference is the units of Y. It's predicted logit. The units of X are still the units of X. Remember, we only translated the left side of the equation. Hours are still hours and tips are still tips. And then we have our odds ratio. An odds ratio, think about an odds ratio. This is 12.63, but how do we usually like odds ratios? Do we like them as decimals or numbers, or do we like them as fractions? Fractions, because odds ratios are odds of event A, which in this case is staying, compared to odds of event B, which in this case is leaving. What is 12.63 in fraction? Thank you. 1. For every 1 more hour, you are 12.63 times more likely to stay. So if you want to think about it, not everybody thinks about it this way, but if you want to think about 0 as leaving as the reference group, you can. The non-desired outcome is our reference group. A 1 unit increase in hours means you're 12.63 times more likely to stay. You're 12.36, it's like 12.63 times more likely to go to the desired outcome. But the reason I don't call it the reference group is because it doesn't impact the predictors at all. It's only the outcome. If you have an odds ratio that looks like this, let's say the odds ratio is, this is 12.63. Actually, let's do tips because it's a little bit easier. We have 1.03 over 1, staying versus leaving. We could flip that with the phone out, do 1 over 1.03, please.
0.97.
What?
97.
If it were 0.97, it would actually mean that the odds of staying are less than the odds of leaving, as in people are more likely to leave. But whatever you have in the odds ratio number is always towards the desired outcome. You are 1.03 times more likely to stay. If it were 0.97, you could say you're 0.97 more likely to stay, but that doesn't make sense because it's less than 1. We would probably flip it into a fraction and say you're 1.03 times more likely to leave. Yeah. Let's look at the questions and then I'm going to give this 5 more minutes and then we need to switch. This was the example from the check-in. The first question was, what type of analysis should you use to model this relationship? The default, this was looking at financial analysts were interested in building an algorithm that would predict whether bank customers would default on their loans. 0 was no and 1 was yes. The dependent variable is the status observed after the loan's issued, which is a 1 if they're a defaulter and a 0 otherwise. And then the variables are other debt they have, age, years at their address, years of employment, debt to income ratio, and credit card debt. Most people, I think across the board, I think there was one blank answer, but across the board, we were able to identify, yep, this is binary logistic regression because our outcome is binary. And then I asked you specific questions about it. We're going to look at these individually. Here's the first one. The team is debating which model to choose. Each makes a case for their choice and provides rationale. Which choice and rationale is strongest? And then what's the overall classification success rate of that strongest model? The issue with this question for the folks who got it wrong was not choosing the model, it was what evidence to provide. And this is the same thing as what showed up on the midterm. Let's look at model. Model 2 is better than model 1. Model 3 is better than 2. Model 4 is better than 3. Model 5 is better than 4. But what? 6 is not better than 5. What's the best model? 5. But what evidence do you have to provide? You have to provide 2 pieces here. How 5 is better than 4 and how 6 is not better than 5. Model 5, it classifies default status significantly better than, why did I write R squared? Should have written chi-square. Oopsies. Significantly better than model 4, chi-square difference, but the addition of other debt in model 6 does not help classify better, does not help predict better. What's the overall classification success rate of your best model? 82%. Now, here are the 3 options for answers for this. I didn't generally, when asking for classification success rate, we're going to report it in percent because we want to know what percent of the time did the model classify correctly. The best answer here would be you could do 82, you could do 81.71%, you could do 0.82, you could do that's it. A lot of people are just like 0.1, let's cut it off. Nope, it's 7 rounded up. Any of those are fine. No 0, why? Can't be more than 1. According to the model, you suggested the strongest predictor of defaulting on debt is what? This one is 1 difference from multiple regression. Normally, we look at what in multiple regression to get strength? Beta. Here, we can't look at odds ratio. Why? Good, they're unstandardized, you can't compare them. In fact, remember the example with tips and hours? It looked like hours was way stronger, but that's because it was a 1 hour increase versus a $1 increase. Very different. You cannot use odds ratios, not for strength. What is for strength? Good. Why? How are Z's? Here's a good question. How are Z's similar to betas? They're both standardized. What it's doing is standardizing the strength of all of these predictors. Okay. In a regression, we could look at the T if we wanted to determine strength, just like here we can look at the Z, but the T doesn't help us see slope. We can just kill 2 birds with 1 stone and look at the beta. But here, the answer is not, a lot of people put credit card debt. No, the answer is employment. Because credit card debt is like in the units of, that odds ratio is for every 1 more unit of credit card debt, whatever unit that is, versus employment is for a whole nother year of working in that job. And that's a stronger predictor. I have this on the next slide, but let's look at here. What was 0? Do you remember? For defaulting? No, it would not. It was no default. And a 1 is default. Now, notice, very interesting. Credit card debt, their Z is 6.54. Their coefficient is 0.57. And the odds ratio is 1.77. Compared to employment, the coefficient is negative 2.26. The Z is negative 8.66. And the odds ratio is 0.77. What's different? Yeah, when you have a negative coefficient, how do we interpret that? For every 1 more year of employment, holding everything else constant, your predicted logit goes down, as in your probability of defaulting goes down. Your odds ratio is less than 1 because for every one more year of employment, you're 0.77 times more likely to default. That actually makes you less likely to default. Yes, asked when the coefficient in Bilo Ray is negative, will the odds ratio be less than 1? Yes, always. Cool. Borrower A is 25 and borrower B is 27. Assuming they have the same years at their current address, same years at their current employer, same debt to income ratio and credit card debts, borrower B is blank times more likely to default on their loan than borrower A. Remember that odds ratios are for every 1 unit increase in blank, you're this times more likely to be the positive, the desired outcome. We go down to our odds ratio and it's age. We have 1.365. We're going to do, that's for how many years? One. That's for 1 year. For every 1 year increase in age from 25 to 26, you would be 1.37 times more likely to default. But it's 2 years difference. What do you have to do? Multiply it. 1.3656452 times 2 year difference between them. A lot of people just missed. Oops, it's actually not a 1 year increase, it's a 2 year increase. Again, do this out before you round. Questions at all? There's one more slide. Last bit of general review on Bilo Ray, and then we'll take a break. These are based on questions that you asked in the Qualtrics that I didn't explicitly already cover. The first one is obvious but hard to explain. Why can't we use OLS? I already mentioned this, but OLS assumes it's continuous and can take on any value. The Y can be anything. If we use OLS, you can predict probability models or values like -1.3 or 2.7 or 3.9, none of which are possible when you're talking about probability. In Bilo Ray, does a -B actually predict the reference group? Would the odds ratio reflect that by being less than 1? Yes. In Bilo Ray, when determining your base rate by looking at the frequency table and your descriptives, how do you determine which percentages applies to which outcome? You have to be told. It has to tell you what's labeled 0 and what's labeled 1. If it doesn't tell you, I will tell you. But if you got data that didn't tell you, the best assumption is that the desired outcome is labeled 1. If you're trying to help a restaurant keep their people, you can assume that staying is 1 and leaving is 0. But in an exam format, I will tell you what's labeled 0 and 1. How is the intercept interpreted? We talked about this. The same way. It's the predicted value of Y when all predictors are 0. The Y in regression is just units of Y. The Y in Bilo Ray is logits. For binary regression, what is B good for? I love that question. Nothing. Just kidding. This is your whole damn model. Those are your parameter estimates. That's the thing that tells us the relationship between our predictors and our outcome. This question is a good example of forest trees. What is it good for in terms of us? Like calculating values by hand? No, not much. But it's the entire model of how your predictors are related to your outcome. It is the thing that is going to be used to predict probabilities of that binary outcome. And then last, is Bilo Ray like moderation in that you deal with mostly centered data? No, you can run Bilo Ray centered or uncentered. There's no moderation. Well, you can run a moderated Bilo Ray. You could run I wonder if hours to staying is moderated by tips. You would run it exactly the same way you run a regression model. The only difference is your outcome's binary. So if you did this, yes, center, you have to. But if you ran a main effect model with hours and tips predicting staying or leaving, you can choose. It depends how you want to interpret the intercept. But it doesn't have any statistical consequences if you don't center, if it's main effects. As I said before, regression and moderation, regression with main effects only, and then rather than thinking about it as regression and moderation, they're both regression. But one is modeling only main effects and one is modeling main effects and interactions. Both are on the exam. We're going to start with main effects only, and we're going to use first start with this model selection question. The researcher tests the 5 models, exploring predictors of job satisfaction using the output. Which model would you conclude is best? We're going to go straight to model. Just a quick reminder when reporting, because I saw this in a couple of the other questions that asked you to report the R-squared. These are the R-squareds of each model. This is the variance explained by each model. This is the delta R-squared. This is the difference between model 1 and model 2 and model 3, model 3 and model 4, model 4 and model 5. If you were to literally subtract the variance explained by model 5 from the variance explained by model 4, you would get that delta R squared. When we're reporting model, we don't report the model variance. We report the difference between 1 and 2 is significant. The difference between 3 and 2 is significant. 4 is better than 3 and 5 is better than 4. 5 is our best model. If we were reporting this with stats, like if this were like report all relevant statistics, you could say model 5 explains significantly more variance in job satisfaction compared to model 4. And the stats you would provide would be delta R squared 0.01, P less than 0.001. And then because there are many models before and nothing after, it's going to say model 5 explains significantly more variance in satisfaction than model 4. Stats, which explain more variance in job satisfaction than all previous models. You can just do that for the other 4. Because there's a lot. You don't need to report all 5. Let's look at multiple regression with categorical predictors. This is the cognitive psychologist who's interested in predicting reading comp. For kids, he collects the following variables: vocab, sustained attention, and SES, which is categorical, low, medium, and high. And he, reference group is low. Reference group is low. You can tell by the predictors that are labeled in mid and high. What we're gonna do here is exactly what we talked about in the forest through the trees slide. We're not going to go to the questions. We're going to wrap our head around the research first. Here's our theoretical model. But this purely theoretical model is not helpful for labeling coefficients because how many, other than the intercept, how many do I have? Count. 4. How many arrows do I have in my purely theoretical model? Don't match. Doesn't help. I'm going to redraw it. I'm going to redraw it like this. Now, so we talked about the idea of like, well, when do we use B's and when do we use betas? Well, first of all, when all you have is B's or all you have is betas, that's one time. In this case, we only have B's. However, in general, whenever we're talking about relationship, betas are preferred because you can interpret them. If you have them, label your model with betas. If you don't have them, you have to label your models with B's. B's are really helpful when predicting values by plugging in, but that's about it. How do we label this? Just go value by value. 90.31, that's the intercept. I'm going to put that over here. That's the predicted value of Y when all X's are 0 or centered or average, depending on whether we centered. Then 1.52 is the relationship between SES and mid, and 2.31 is the relationship between SES and high. Notice here, I put a 0 and a 1 again. But when we dummy code, the red stars, those are your predictors. When you plug in predictor for SES, what 2 values can you plug in? 0 or 1. And because of that, these are always going to be constants. 1.52 and 2.31 or 0. That's it. It's the only value they can take. And if they become 1.52, the only place that can go is here, added to the intercept. I'm going to label that 0, 1, so I don't forget that. Then the slope between vocab and reading comp is 0.29. The slope between sustained attention and reading comp is 0.14. Question for you. Is there anything pointing at the slope between vocab and reading comp that would change it like that? No. What is the relationship between vocab and reading comp no matter what? 0.29. It's never going to change. This is why we draw it like this. If it doesn't have anything pointing and hitting the line, that slope doesn't change ever. What it did was it got all of the people in the study together, regardless whether they were low, medium, and high, and it fit one slope that worked best for everyone. That's it. That's the idea of a main effect. The slope does not change based on SES. That would be a moderation model. The expected reading comp score for a student with low SES, average vocab, and average attention is what? Well, if the data are centered, which I think it said, then what are we plugging into everything? Great. 0, 0, 0, 0. What are we left with? 90.31. Great. What's the expected reading comp score for a student with middle SES, average vocab, and average attention? Average vocab, 0. Sustained attention, 0. SES mid, what are we plugging in? 1. Here, I'm choosing the 1. And what about for SES high? 0. The only thing left is 1.52. That gets added and we get 91.83. The slope of the line depicting the relationship between vocab and reading comprehension for students with high SES is what? 0.29. It doesn't change. There's nothing that hits it. What's the relationship for students with mid SES? 0.29 doesn't change. What's the relationship for students with low SES? 0.29 doesn't change. You notice that you can answer every single one of these questions just with your theoretical model labeled. That's true in moderation too. You literally don't need anything else because this is conceptualizing what's happening. This is the holistic thinking. This is the forest view that tells you, I'm just looking at the main effects on reading comp. There's nothing changing the relationship between vocab and reading comprehension. That's one relationship that applies to all the groups, rather than what two numbers should I add to get the expected value. Use the full research context to answer the questions. What is B and beta? It's the parameter that are estimated for you. It's considering the impact of everything else in the model. When you are evaluating a B or a beta, it is holding everything else constant when it's a main effects model. You could say the slope between X and Y, holding everything else constant, how X and Y covary together, holding everything else constant, the change in Y for a 1 unit change in X, holding everything constant, the relationship between X and Y, holding everything constant, or the effect of X on Y, holding everything constant. Now, what do I mean by holding everything constant, and why do I say constant here and average and moderation? That's another example of tunnel vision. Like if you're trying to memorize where you say constant and where you say average, you're not forest, you're trees. It's a very easy question if you go to forest. Let's look at what holding constant means in the context just of multiple regression. Here's a model. Miles walked per day and hours of sleep predicting mood. If we want to interpret the unstandardized regression coefficient for miles, we would say it's the relationship between miles and end of day, holding hours of sleep constant. Doesn't matter what that hours of sleep is, it just has to be the same. Let's look at two examples. Our slope is 1.25. For a 1 unit change in miles, 1 unit change in miles, the difference between me and my wife should be 1.25, yes? But only when hours of sleep is held constant. Here's two examples. I walk 4 miles, she walks 5 miles, we both sleep 5 hours. Here's another example of holding constant. I walk 4 miles, she walks 5 miles, we both sleep 9 hours. Not constant, I walk 4 miles, she walks 5 miles, a 1 unit change, but I sleep 10 hours and she sleeps 3. It's probably the other way around, to be fair, but I sleep 10 hours and she sleeps 3. Look what happens to our predicted mood. Here's the equation. Look what happens. If we plug these values into the equation, in these two models, when sleep is held constant, what is the difference in mood between Myra and I? 1.25. The predicted change in Y for a 1 unit change in X, holding the other one constant. But if I don't hold it constant, if I mess with the other variable too, then it is not a 1.25 difference. It's a 18-point difference. And now there's still a 1 unit change in miles, but I didn't hold sleep constant. It's not the expected difference in Y anymore. That makes sense? We'll get to the average in a second. Main effects with interactions. Any questions before we move on though about this constant thing? Super important. Notice it doesn't need to be, the key point here is it doesn't need to be, the other variable doesn't need to be at a particular level. It doesn't need to be average, it doesn't need to be high or low or anything. It just needs to be held constant, controlled for, accounted for. Why? Because hours of sleep is not touching miles per day. It's not here. It's not going to change that slope. It can be high, it can be low. The slope is still 1.25. Now moderation. Any questions about the constant? Does that clarify a little bit? Why center and moderation? Is this the most important thing? No, but it is important actually in the context of moderation. It has two very important impact. One is statistical and one is conceptual. Two, why we center. Statistically, it will help us reduce multicollinearity. I put next slide because I knew there'd be like, but how? Yes, it helps us reduce multicollinearity. Don't worry, this is the same last year. It happens every year. And then the second is conceptual, which is that if we center, then we're talking about when the other variable is average. And that's important because it allows us to see the effect of X on Y at the average level of the moderator, which is a really helpful reference point compared to high and low. If we didn't center, we'd be looking at the effect of X on Y when the moderator was 0. And that's not very helpful. I have that on a slide too. Number 1, why center and moderation? Statistical, it helps with multicollinearity. We remember what multicollinearity is. It's how related our predictors are to each other. We do not want to build a model with predictors that are too related to each other because it will inflate variance. Explained. I'm going to show you one way of thinking about how it reduces multicollinearity. Here's our raw data. We've got X, the mean is 4. We've got Z, the mean is 6. And we've got a moderation. This is if we did not center. We just multiplied those together. What I want to do is, if moderation or if multicollinearity is how strongly predictors are related, let's plot the relationship between X and the moderator to see how strongly they're related. This is what it looks like. When you plot each of these points, 2, 8, 3, 15, 6, 48, 5, 35, 7, 63, it is a perfectly linear relationship. And when you actually ask for the R coefficient, it's 0.99. Super related, i.e. collinear. Watch what happens if we center. We're going to center. Here's X centered. We subtracted the mean. This is 1 point above the mean. What would centered score be if they were average in X? What would centered score be if they were average in X? 0. If we had a 4, if this was a 4 instead of a 7, this would be a 0. We've centered our X. And we've centered our Z, and here's our moderator term. Now I'm going to plot the same thing. X centered related to our moderator term. Here was negative, and we got a positive number. Here was negative. Here was negative, and we got a positive moderator. Here was negative, and we got a positive moderator. Here it was positive, and we got a positive moderator. Look what happens when I plot these. Guess what the correlation is? 0.61. I have massively decreased the relationship between predictor 1, which is X, and predictor 2, which is the moderator term, i.e. they are not as collinear as they were when they were not centered. Does that help? That's a good question. The problem with collinearity and moderation is not between your individual predictors. If your individual predictors are really highly related, that will still show up when centered. So if we did height, if we did like feet and inches and then created a moderator term, we would reduce multicollinearity with the moderator, but we would not reduce the issue of feet and inches. That's going to stay. Well, the problem that we have is that we're artificially creating a multicollinearity problem with the moderator term because we are literally taking two things and creating that as a product of them. We're essentially undoing the problem we create. That make sense? Cool. That's the statistical. What is the conceptual? The conceptual is that it allows us to see the effect of X on Y at the average level of our moderator. Let's say we're working with the unstandardized equation or the standardized equation here. No matter what, this B1 is the effect of stress on psychological well-being when support is plugging in a 0. We plug in a 0 for support, we plug in a 0 for support, this goes away, and we're left with B1. Now, for looking at simple slopes, if we really used uncentered data, then B1 would be the relationship between stress and psychological well-being when support is nothing, 0. Let's say you like measured on a scale of 1 to 7, then that's a meaningless number. And the high support simple slope would be the relationship between stress and psychological well-being when support is 1 standard deviation above 0. That's probably a meaningful number. But look at what the low is. It's the relationship between stress and psychological well-being when support is 1 standard deviation below 0, as in negative. How do you have negative support? If support is on a scale of 1 to 7, this becomes not meaningful and this becomes not meaningful. But if we center first, then plugging in a 0, which is actually a centered 0, which is the mean, who has the mean, then we can interpret the simple slopes, the relationship between stress and psychological well-being when support is average, and then compare that to 1 standard deviation above average and 1 standard deviation below average. From a forest perspective, that allows us to understand how support actually changes the impact of stress on well-being. This does not. Make sense? It's not like, it actually is really important to center in moderation to understand the model of the real world you're trying to do. If you don't center, it makes it very uninterpretable. Whereas with the main effects model, your intercept becomes uninterpretable, but we don't really use that for a lot of things. Now all we have left really are the questions from the end of module check-in that had to do with moderation. This is the model, stress to psychological well-being. The very first thing we're going to do is we are going to label our coefficients. First we have a model to moderate the relationship between stress and psychological well-being for adolescents. Provide the best statistical evidence to support your conclusion. Notice the percent correct here. It's pretty low. However, if the question were just moderate the relationship, yes or no, the question would be 100%. The issue is not recognizing whether or not there was moderation. The issue is providing the statistical evidence and writing it correctly. Here we have our model fit, and here we have our model coefficients. How and when do we decide there's moderation? At what stage? Model fit or model coefficients? Model fit. Model fit is where we look for moderation. Model 1 and Model 2 are main effect models. Model 3 has the main effects and the interaction. Is Model 2 better than Model 1? Yes. Is Model 3 better than Model 2? Yes. What is the only thing we added between Model 2 and Model 3? The interaction. Did adding the interaction explain significantly more variance? Yes. That's our evidence. A lot of people just gave this, which, although it's true that the significant moderator indicates significance of moderation in that model, you want to always compare the full main effect model to the interaction model. We don't use the beta to support the interaction. Yeah. How do I report this? Yes. The model with the interaction explained significantly more variance in psychological well-being than the main effect only model. And then the stats, you cannot just provide the p-value. You need to provide the change in variance explained and the p-value. Delta R squared equals no leading zero, 0.007, round to the first significant digit, or if you said 0.01, that's fine. 0.007 or 0.1, and then P equals 0.004. Coefficients. Forest first. Before we do anything, we're going to draw our model and we're going to label it. You can draw it both ways. You can draw it unstandardized, so it looks like this, or you can draw it standardized, so it looks like this. Generally, if we want to talk about relationships, betas are way more helpful. If you get asked about predicted values, ask this question: when are B's versus betas helpful? If you're dealing with slopes or relationships, betas. If you're reporting strength of predictors, betas, because those are slopes. If you're predicting values, B's. That's it. Why? Because B's are in units of Y. In this case, B's are telling us predicted well-being scores in well-being scores, like 1 to 7, versus standardized is telling us predicted well-being in standard deviations of Y, which is hard to interpret. That's the only. We're going to label them first. We've got our main effect of stress, our main effect of support, pink and green. And then we have our, I didn't add this, but probably good to do it. This is our change. Were they really the same? Yeah, they were the same. They happen to be the same. That's a coincidence. That just happens that way because of how they were measured. Now, once you do this, you can calculate your simple slopes. You should calculate your simple slopes first. What's the relationship between stress and psychological well-being when support is average? What's the relationship between stress and psychological well-being when support is average? Thank you. Negative 0.22. Negative 0.22. What about when support is high? We're going to take negative 0.22 and add 0.09. What about when support is low? We're going to take negative 0.22 and subtract 0.09. When support is high, that negative slope gets less negative. Yay, support buffers. When support is low, that negative slope gets more negative, meaning stress has an even greater negative effect on psychological well-being. Yeah.
For the rounding, for rounding purposes, we wouldn't, this is like nitpicky, but we wouldn't, we would use it online instead of 0.0855.
Yeah, for this, it's fine. Yep. Again, this is what I did do it on the next slide, haha. This is how I would sketch before I ever start answering questions. I would say when it's average, it's negative 0.22. The intercept for that is 0, because when it's standardized, the intercept is always 0. When it's high, it's going to be negative 0.22 plus 0.09, which is negative 0.13. And the intercept, look at that. I plugged in a 1 because I'm going 1 standard deviation above. 0.32 times 1 gets added to 0. It's a third of a standard deviation higher. And then when it's low, I subtracted negative 0.22 minus 0.09, and the intercept is minus 0.32 standard deviations. I can draw this whole thing. Do your intercepts need to be perfect? No, not at all. Not at all. But your slopes should look how the degree of the relationship. Negative 0.13 is a little bit negative. Negative 0.22 is more negative, and negative 0.31 is even more negative. And I'm going to label them high, average, and not high, low. Do this. Now, what's the story? Before you ever answer questions, what's the effect of support on the relationship between stress and well-being?
Negative effect on well-being. But
Stress has a negative effect on well-being. Good. I like that you started with the main effect.
to support at higher levels to support that negative relationship.
Beautiful. There's a negative relation. Stress has a negative effect on well-being, but at high levels of support, stress has less of an impact on well-being. Or at high levels of support, that relationship is buffered. We don't know if it's buffered completely because we don't have p-values for our simple slopes here. This is just a sketch. This is us wrapping our head around the research, but we do know that it gets less negative. Yeah.
I guess I was wondering why can't we just say in general it buffers it? Like why we have to specify that it's at a high level?
You could just say, yeah, because we know a lay audience knows that support is a good thing. Yeah, you could say support buffers the negative effect of stress on well-being. Yep, totally. That's like just a more concise way of saying. Good. This is for a 1 standard deviation increase. If you wanted to know for a 2 standard deviation increase, you just add another point. In model 3, the unstandardized regression coefficient for support is 0.34. Concisely explain what 0.34 means to a psychologist who is not familiar with statistics. This was the lowest question on the check-in. There's a couple things that make this, there's one thing that makes this challenging. How did we set up the theoretical model? We set up the theoretical model with support being the moderator. But under the hood, this model mathematically is the same as this model. Why? Because this is how we draw it for us. But that's not what's actually being in R. You can't regress onto a line in R. What's actually happening in R is well-being is the outcome. Support is one predictor. Stress is another predictor. And then the interaction between support and stress is the third predictor. R does not care whether it's stress times support or support times stress. How do we always interpret either main effect? It's the relationship between support and psychological well-being, but only when stress is average. If stress changes, that 0.34 is going to change. Just like here, the relationship between stress and psychological well-being is negative 0.23, but only when support is average. This is the forest through the trees. It's moderation. Main effects are not main effects. They're main effects as if the moderator doesn't exist, but the moderator is in your model. If you have this, look at this term has both of them in there. It's going to change both these slopes depending on how you set it up. The definition of an interaction is your main effects don't, if your moderator is any other level than average, your slopes as estimated will change. That 0.34 and that 0.23 are only the relationship when the other is average. And that's what people missed. People did fine saying for a 1 unit increase in support or in stress, people were fine with that. It was the average part that was missing from almost everybody's. Constant for multiple regression, doesn't matter what it is, just has to be the same. But for moderation, since the whole point is changing slopes, it's only when the moderator is average. How do we explain unique variance explained by a single predictor? That's the first piece of knowledge that people forgot. It's not beta, that's the relationship. It's beta what? Squared. Just like when we want to know, otherwise we're double counting. It's covariance. Covariance is beta. This is how the moderator term and the outcome covary. But we're double counting. We just want to know how much variance in the outcome is explained by the predictor. Unique variance explained is 0.08551731 squared, which means I'm going to multiply 0.08551731 times itself, and I get 0.00731223. But what does the question ask for? Percent. What do I have to do? Multiply it by 100 or just move the decimal place over? To get a percent, we have to multiply it by 100 and we get 0.73%. Percent as a number can go from 0 to 100, but gets a leading 0. And this was tricky was because if you rounded first, you get a totally different answer. It's 0.81. I had to write out, and people put leading 0, people didn't. People rounded to like 3 digits, which actually gets you 0.72 instead of 0.73. Yeah, it's fine. Not a big deal, but 0.73. The key knowledge here though, that I want you to focus on is not rounding. It's the idea that in order to get unique variance explained, you need to square your beta, just like we had before the midterm. The relationship between stress and psychological well-being for who has high support, 1 standard deviation above the mean, is what? By this point, you should have this drawn. And you're like, I already know that. When support is high, the slope is negative 0.13. I should just put that down. You've already figured out the story. You're just writing in the answer. Make sense? Any questions about how I got negative 0.13 here? This is it. Last time you have me online.
Jess, I just
I
have
can
a
see your
quick question
faces.
on that.
Yeah.
You had the y as 0.320 and negative 0.32, I think, on the prior, or for the intercept, I think.
This one?
It was on the prior slide.
Like before this?
Yeah. Yeah.
Here?
Yeah. Can you just explain that y one more time?
This one? Or
In the green on the simple slopes drawing, y equals 0.32, y equals 0, y equals negative 0.32.
the intercept is 0. Why? Because you've standardized your y. Your predicted y, when all your predictors are average, is the average of y, which is 0. You've standardized it. It's like you have a 0 here. There's no intercept, which means that for the average line, you're starting at 0. But if you plug in a 1 standard deviation for support, that means you're plugging in a 1 down here, a standardized 1. That 0.32 is a constant now. It's just 0.32. Has nowhere to go except be a number. What's the intercept when stress is high, or when support is high?
I got it.
Right?
Thank you.
But it's in standard deviation units. When support is high, that line starts about 1/3 of a standard deviation above the average line. That makes sense? If you get a question, like if you do all this first and you wrap your head around the research, then you already know all the simple slopes and you already know all the intercepts. And you've made sense of the research of like, this is actually what happens to this relationship out there in the world when this moderator thing is high versus what numbers do I plug in? Predicted psychological well-being of an adolescent with average stress and average support is what? The intercept. We know our data is centered because it's always centered in moderation. You could either just remember that, or you could think your way to it if you forgot. An intercept is always the predicted y when all predictors are 0. What are you left with? Negative 0.003. This was another rounding issue. You round to the first significant digit, it's negative 0.003, 0.003. Question about this one. Growing up, Jess was only allowed to learn to drive manual transmission cars. This is true. And to this day, she swears they're better than automatics. True. To support her claim, she collects data on 32 automobiles, including fuel consumption, aspects of the car's design, and performance. Her hypothesis is that the influence of weight on fuel consumption depends on type of transmission, with 0 being automatic and 1 being a manual. Here is her model. What form of equation did I give you? Unstandardized. Did I give you coefficients? Did I give you a coefficient table? No, I only gave you the model in equation form, which means that's all you have to work with. That's what you're going to use to label. What's the research question? There were a lot of versions of this. Most were fine. Does the relationship between car weight and fuel consumption depend on type of transmission? Or is the relationship between car weight and fuel consumption moderated by transmission? There were a lot of variations of this. Most of them were fine. Before we do anything else, we're going to get to know our research. Forest first. Using the equation, we're going to label my model. 31.42 goes over here. Negative 3.79 goes over here. 14.88 goes over here, but I'm gonna remind myself that I can only plug in a 0 or a 1 there because it's a dummy coded variable that is 0 or 1. A 1 means manual, a 0 means automatic. I've labeled that for myself. And then we have our change in moderator, our change in moderator. The next thing we're gonna do is figure out how does transmission moderate the relationship before we ever go to questions. The first question is, well, what's the relationship between weight and fuel consumption for an automatic? That's the first thing we're gonna figure out. Well, it's 0 plugged in here. That would be an automatic. That goes away and that goes away. And we're left with negative 0.379. A lot of people, not a lot, people put 3.79 rather than negative 3.79. Those are really different relationships. Positive, that they're the same strength, but different direction. And remember, slope is strength and direction. If it were positive, again, that's forest trees. Yeah, the forest here is as your weight goes up, your fuel consumption goes down. Think about how cars work. Big, giant, heavy cars get less fuel consumption. That makes sense. If it's 3.79 and it's positive, that means as your car gets ginormous, your fuel consumption gets better. Nope. Again, forest trees. Second is figuring out, well, what is the weight to miles per gallon relationship for a manual? Well, we're gonna plug in a 1 here. Again, if you find it helpful, you can label this a delta. Bren had a really good idea with a categorical variable, which is labeling this a delta too, because that's actually always just gonna be a change in intercept. It's a good trick for categorical. Negative 3.79, you're always gonna add on the change. Just to make it really clear, I still used an add-on addition, but you're adding on a negative number. You end up with negative 9.9. Again, I saw 9.9s, negative 9.9. If you were to think about what those slopes look like, we don't know what they are standardized, but negative 3.79 is negative, and we don't know how steep, but we do know that negative 9.9 is negative and steeper, even if we don't know what the betas are. And then because we can, the predicted miles per gallon or fuel consumption for an automatic average weight, just the intercept. Why? Because I'm plugging in a 0 here, which means I'm not directly changing this original intercept. But a predicted fuel consumption for a manual with average weight, I'm plugging in a 1 here, which means I'm going to add on 14.88 to where I started, and I get 46.30. That now you know. Tell me, how does transmission impact the relationship between weight and fuel consumption? You know, because it's about the research, not the test questions. Take a second. Start with the main effect and then go, this is the way to do it. Start with the main effect and then just go simple slope by simple. This is your story here. How does the relationship between weight and efficiency change depending on whether I decide to buy a manual or an automatic?
More like better miles per gallon, more miles per gallon.
Yes, except we're interested in the relationship here. We're interested not in just in general, the main effect. There is a main effect of transmission. In general, manuals get better miles per gallon, but that's not what we want to know. We want to know how that interacts with weight. If I buy a lighter versus heavier car and I have to decide whether to get an automatic or a manual, what happens to my fuel efficiency? You could add that as a sentence though, it's totally true. Yeah, say that really loud.
Weight negatively affects fuel efficiency, but it's worse for manuals or automatics.
Perfect. Weight negatively affects fuel efficiency. It's better. Weight negatively affects fuel efficiency or negatively affects miles per gallon. That's a negative relationship. But that negative relationship gets worse when you switch from a what to a what? Automatic to a manual. That's a perfect synthesis. Started with, hey, it's negative for both. No matter what, the heavier your car, the shittier your miles per gallon. But guess what? It's worse when you have a manual. Perfect. Now we can answer the questions. Below is a graph of the simple slopes. Label each. Well, you told me what the simple slopes were. Negative 3.79 for an automatic and negative 9.9 for a manual. Which one's steeper? Blue. That's a manual. And that is an automatic. Now, here is Allie's observation in action, which is, but look where manuals start. There's a main effect of transmission. Manuals start with way better miles per gallon than automatics do, but it decreases a lot faster with weight. Good. The simple slope between car weight and fuel consumption for cars with automatic, I'm literally just taking what we already did, and it's negative 3.79. The simple slope between car weight and fuel consumption for manual, negative 9.09. The predicted fuel consumption for an automatic car of average weight, we already did that too. It's like plugging in a zero, 31.42. And for a manual, 46.30. This is why you sketch first, because the story here, big picture, is now this was sketched for you, but you could have sketched it yourself. You said the intercept for manuals is a lot higher than the intercept for automatics, but the slope is a lot steeper. Well, what does that mean? It means that in general, when weight is average, manuals have better miles per gallon than automatics. But if you go up in weight from there, that efficiency decreases much faster for manuals than it does for automatics. That's the whole story. This one, moderation backwards. Close. We were close in a lot of places. If we had double checked, we would have been much closer. You can double check whether you get these, plug them in. Positive psychologist is interested, by the way, you've not seen this 3 times. You can assume that this might be you need to know how to do. A positive psychologist is interested in how expressing gratitude, writing a thank you note, impacts of well-being. She hypothesizes that the target of the thank you note, family, friend, coworker, will change that relationship. How's the little battery? I'm plugged in. Using the following results from her study, create the regression equation, predicting well-being from expressing gratitude as moderated by target. Note that coworker serves as the reference group. The first thing I did here was I wrote out the equation and I drew the model and labeled it with the coefficients. Now, the coefficients are just B's now. They're not labeled numbers yet, because once I figured out what those numbers are, then I know the whole equation. But I'm working backwards because my final equation should have this many terms: an intercept, a main effect of, God, how about I change that real quick? I didn't change the names. You can do that. Okay, better. I'm gonna write them out first. What happened to my B? Screw it. I'm just gonna, don't forget we have our B here. Why did I only write B's and not betas?
That's all you gave us.
What?
That's all you gave us.
Yeah, that's all I gave us. I have average scores, which means I have intercepts for all 3. If the intercept for the reference group is not 0, that means I'm dealing with unstandardized. And more importantly, I told you that that's all we have. I have to figure out what those coefficients are. The coefficients in my model should match the coefficients in my equation, as in numbers. I've got 1, 2, 3, 4, 5, 6. I've got 1, 2, 3, 4, 5, 6 in my visual model. Now I can start to fill them in. First of all, key to understanding how to do this is, what is this table? It's descriptive. It's meaning it's the actual values of the relationship. It's not change in slope. It's not coefficients. It's actual, the relationship between gratitude for well-being when is writing to a family member is 0.68. These are not changes, and these are actual slopes. We start with our reference group. Our reference group is what for friend and family. What do we plug in for friend and family? Remember that our reference group is like we don't have a moderator. If I scribble out these 2 sectors, what 2 coefficients are left? The intercept and the main effect of gratitude on well-being for the reference group. We know the first 2 terms, y equals 4.85 plus 1.37 gratitude, okay? A lot of people miss the gratitude part. Now we need to deal with these green B's and then the change moderation B's. This is, I think, where Bren's trick of deltas on the intercept with categorical is super helpful. If we add a little delta here, because remember, these values can only be 1 or 0. If we put a 1 in for friend, this is going to become value that gets added where? To the intercept. And the new intercept is going to be this 4.85 plus, that gets us to 4.93. How do we get from 4.85 to 4.93? Just say it. 0.08, friend. And then you can test it. Look, if this is 0.08 and the intercept is 4.85, well then when we're writing to a friend instead of a coworker, this is going to be 1, which means this 0.08 is going to get added to here. And what do we get? Oh, 4.93. Same thing here, times 1 added to this 4.85 is going to equal 5.67, which is the intercept for family member. What is that? It's 0.82. I looked at a lot of these, like I remember the coefficients. Now we have the same concept with change in slope. We have, and this is where a lot of people got it, but for the signs were wrong. We start with a slope of 1.37, that's over here. When we move to friend, that 1.37, this is the 1.37, we can label it now. That 1.37 gets hit by, and it gets changed to what? 0.93, which means the change has to be what? Negative, because it goes down. It's negative 0.44 friend times gratitude. And the same thing happens here. We start with 1.37, it gets hit by coefficient and it goes down to 0.68, which ends up with, is it 0.69? No, yeah, I really did memorize those coefficients. That's sad, right? 0.69 family times gratitude. Now, what am I done? Should I finish now? What should I do? Should I be done? Should I go to the next question? I was like, yep. No. What should I do?
Plug this in and check them.
There you go. Put the betas in your theory, in your model now. Label it with what you decided were the coefficients and check. Watch what happens if I do that. If I'm like, the starting is 4.85, this is 1.37, this is 0.08, this is 0.82. Let's say I screwed up and I said this was 0.44 instead of negative. Well, then guess what? I'm like, when friend happens, 1.37 plus 0.44, that's not 0.93. I screwed up. Check it. That's it. Last part of moderation and then we'll be done, which is just a couple notes about storytelling. A lot of you have asked about like, when do I say strengthen, weaken, buffer, amplify? Again, that's not a memorization question. That's a like Forrest. Context agnostic. Forget context for a second. Strengthen and weaken have to do with not direction, but strength. Remember, slopes can be positive or negative. That's direction. But regardless of their direction, they can be really high, like value close to 1, or really low, value close to 0. Strengthen and weaken, context agnostic, have only to do with strength. For example, if you're strengthening, if a modifier is strengthening, that means it's making it either more negative or more positive, either way. Whereas weaken means that as the moderator goes up, the slope is getting less negative or less positive. Now the question is, well, when in context do you use things like amplify or strengthen in a positive way versus things like buffer? Well, it depends if you're talking about a desired relationship or an undesired relationship. If you're talking about a desired relationship, as in this thing makes this other good thing even more good, then when strengthens, you want to use the word amplify. You could use the word strengthen, that's fine. But if it makes it go down, that would not be good. You wouldn't say buffer because it's not a bad thing, it's a good thing. You would say, man, I'm bummed, it weakens it. But if you're talking about buffering, buffering is only when we're talking about an undesired relationship, like stress on burnout or stress on quitting, like things you don't want to happen. Then good things can buffer that, as in make them less negative, usually, or make them less positive. If it's stress and burnout, that's a positive relationship, but we'd like to make it less positive. That makes sense? It's all research context. Last thing I think this is the very last slide. One other thing about storytelling, which is when you do, up until this point, I have not shown you an actual simple slopes analysis. Do you notice that? A simple slope is the effect of X on Y at a particular level of Z. When we have a moderation, like the example you had in DA4 with family adversity, child aggression, and positive peer relationships, how many simple slopes were we looking at? 3. The effect of family adversity on childhood aggression when positive peer relationships was average. That's one simple slope. A second simple slope is family adversity on aggression when positive peer relationships are high. And then the third one is when positive peer relationships are low. Taken together, if you were to describe simple slopes here, it would be the effect of family adversity on childhood aggression at different levels of peer relationship. Or if you wanted to be more specific, you could say the effect of family adversity on aggression when peer relationships are low, average, and high. In DAs and on the exam and in real life, you actually get to test those simple slopes we've been calculating by hand all the time. And what we're testing is very important, which is that slope, here is low and high. Low is 1.069. This is average in pink, and low is negative 0.23. Let's round correctly. Since I gave you so much shit for doing it, I might as well do it too. Don't want to be a hypocrite. Great. And I put a 0 there because we know it's unstandardized since I've got above 1. So there are my slopes. We can see what happens when positive peer relationships are high. This is high, low. Whoa, that relationship in general, as family adversity goes up, child aggression went up. There's your average line. But when positive peer relationships were high, that slope changed to negative 0.23. Now, the question you have is, wait a minute, does that actually mean that when support is high, that as family adversity increases, childhood aggression goes down? That's weird. The answer lies in simple slopes analysis, which is testing whether this slope and this slope is significantly different from B equals 0. The null hypothesis is B equals 0. And there is because, remember, you've got the slope, but you have what? Error. And that error goes around that slope. And so the question is, together, is it no different than a flat line? Because this is in your sample, but we're asking in terms of inferring out to the population, is there a relationship? How do you tell that? Your p-value. This is my second, other than forest for trees, this is my second tip. Why do you do that? After you label your lines, do that with your simple slopes. Then look at your p-values and label that. This is significant and this is not. What does it mean if it's not significant? It's no different than what? 0. Guess what I'm gonna do? I'm gonna write flat to remind myself that actually when positive peer relationships is high, between family adversity and childhood aggression is non-existent. That's really important when telling the story because buffering buffers a little, but the relationship is still there. And it buffers all the way so that the relationship doesn't exist anymore. That's a different story. Do positive peer relationships moderate? Yes. An increase in positive peer relationship weakens the effect. It was a positive slope, it got less positive, of family adversity on childhood aggression. We don't want child aggression. It's an undesired relationship. We can say that positive peer relationship buffers the effect of family adversity on childhood aggression. But the simple slope in peer relationships is negative, but it's not significant, meaning it's no different than a flat line. We can say not only does positive peer relationships buffer it, but when positive peer relationships was high, family adversity was no longer at all with childhood aggression.